Welcome to week 2 of social network analysis. This is the less mathy version of network modeling. Why do we want to model networks? Because we want to understand the underlying dynamics that lead to the observed structures. So, for example, last week we looked at several networks and observed some interesting characteristics. We thought we understood how girls in a dormitory choose their dining table partners. However, knowing particular values that we measure for one network does not mean that if we go to another dorm, we can predict what those values will be for the other setting. But if we have an underlying model that tells us, well, these are the motivations for the edge formation in that network, then we may very well be able to generalize and make predictions about networks we haven't even yet observed. Now, this is all nice, assuming that your model is actually a good representation. Now, how can you tell that your model is valid? Well, what you're going to do is you're going to generate either through simulation, which is what we'll be doing with NetLogo, or you can derive mathematically properties of networks that follow the dynamics and the assumptions that you make in the model. And if those values agree, if your prediction based on the model agrees with the observed quantities, then your model is a good one. However, if your model fails to predict some features, then you know that perhaps there's room for improvement. Maybe there are additional characteristics that need to be incorporated into the model. So, for example, if in the dining table partner networks that you observe, you see that some girls have many more incoming edges than others. If your model is that partners are chosen at random, you may or may not be able to reproduce that observed degree distribution of some girls having much higher degree than others. So in that case, you may need to incorporate additional features into your model. For example, that some girls are intrinsically more desirable as dining table partners than others are. Or there may be other mechanisms that can lead to this discrepancy or dispersion in the degree distribution. And we will talk about some of those models this week. First, let's talk about the most essential model of networks. And this is the Erdos-Renyi random graph. First, let me tell you about Erdos and Renyi. Erdos is a very famous mathematician who was extremely prolific, wrote, I think, hundreds of papers. And the way in which he wrote them was he would travel from one mathematician's doorstep to the next. And when he arrived, he would say, "My mind is open, let's work together." And after writing a paper or two with that person, he would then go on to the next. And this, as you might imagine, meant that in the co-authorship network, Erdos had an extremely high degree. And in fact, if you look at the whole network, it's a matter of prestige what your Erdos number is. Your Erdos number is 1 if you directly co-authored with Erdos. It's 2 if you co-authored with someone who then co-authored with Erdos, 3, etc. Mine incidentally is 4, and there are lots and lots of people who have an Erdos number of 4. It's not a very prestigious number at all. But by being so productive, actually Erdos ends up being the center of this very large network. Now, one of his favorite collaborators is Renyi. Renyi is credited with the quote that mathematicians are machines who turn coffee into theorems. Together, they wrote a series of papers on the properties of the random graph, which in this course and in general is called an Erdos-Renyi random graph. Now, let's look at what the assumptions of this model are. They're very few. It's just going to be that the nodes are going to connect at random, so any two nodes in the network are equally likely to connect. The network is going to be undirected, so unlike the dining table partners where you had one girl picking another as her favorite, but this not being reciprocated, here the edges are undirected. And the last assumption, or the last parameter, is what the probability is of any two nodes connecting. We'll call this probability P. So for example, any two individuals might have a probability of 0.1 of having an edge, meaning that 1 out of 10 edges that could exist in the network actually do. Alternatively, what you can do is specify the total number of edges in the network. We'll call this M, and then allocate those randomly among all pairs of nodes. Now, what does an Erdős-Rényi network look like? Here I've taken 20 nodes and I've added some edges at random to connect them, the very definition of an Erdős-Rényi random graph. Last week I said that if you apply a spring layout algorithm to a network to reposition the nodes, placing the ones that share an edge close together, this can reveal some of the underlying structure, like hopefully you saw with your or my Facebook network, right? You should have seen interesting communities. However, by definition, the Erdős-Rényi random graph doesn't have interesting structure hidden because the connections are random. So typically when you look at such a network, you're going to see a hairball. Here it's a small hairball. Larger networks, you see a larger hairball. But one thing that is clear and elegant is the degree distribution, which you can derive mathematically, and I show this in greater detail in the mathy version of this lecture. But basically, each node is going to look at n-1 other nodes in the network, and it's going to flip a biased coin. With probability p, it's going to have an edge to that other node. With probability 1 minus p, it won't. And we have then the degree distribution, which tells us for every degree, what is the probability that a node has this given degree. And as we increase the probability from 5 to 20%, we can see the degree distribution shifting to the right. That is, the higher the probability of adding an edge, the higher the degree is that a node is likely to have. And this binomial distribution then is very well approximated by the Poisson, as long as you have a largish network and the value of p isn't too high. Now let's look at a NetLogo simulation of the Erdős-Rényi random graph. As I discussed already, there are just a few parameters to set. We have the number of nodes. Here I've chosen 200 nodes. And we can decide whether we want to set the probability of any two nodes being connected or the average number of edges or number of neighbors per node. Here I'm going to select the probability. And I use this slider to adjust the probability, starting out with just a 0.2% probability of any two nodes being connected in this 200 node graph. I click the link, I can do the layout, and what we see here at average degree 0.3 is that we have many isolated nodes, so degree 0 is the most common degree, and a few dyads, even one node having 3 neighbors. Let's see what happens as we up this probability, maybe to 0.5%. Now we see that the components are growing. We can increase this further, maybe to 1%. And we can observe what happens to the average degree. Let's just pick one more value, maybe 2%. And we should be seeing a denser and denser network. You can try and tease this apart a little bit by adjusting the spring length and upping the repulsion force, just to see a little bit more of the internal structure. However, these Erdős-Rényi random graphs, once they're dense enough, really do look like hairballs. What the degree distribution tells us is how evenly distributed the edges are among the nodes. What is the probability that a node has degree 0, degree 1, degree 2, and all of those probabilities have to sum to 1. And by looking at the shape of that distribution, we can tell whether nodes tend to have approximately the same degree with some random variation, or whether perhaps there's some outliers that have degree much higher than others. So to test your understanding, if you have a network of size n, meaning there are n nodes, any one node can have a maximum of n n minus 1 or n over 2 edges. And just assume that this is a simple graph, meaning that there aren't multiple edges allowed between the same pair of nodes. Now that maximal degree, which is incidentally n minus 1, is not often achieved in an Erdős-Rényi model. If you have some moderate probability of edges between the nodes, here we'll set it to 20% in a network of 50 nodes, what you'll see is that there is some variation in degree, but the maximum degree, 16, is not that different from the average degree of 10, and it's nowhere close to 49, the actual maximum degree. Now, of course, we can vary the parameters, so we can up that probability to be 0.9. That is 90% of pairs of individuals are acquainted in this network. And now you do have several individuals having the maximal degree, but that maximal degree is not that different from the average. So in an Erdős-Rényi random graph, the degrees of the nodes tend to be pretty similar. You don't have one node having degree 49, and we might call that node a hub, and everyone else having degree 1 or 2. So, to further deepen your understanding, I'd like you to figure out what the approximate average degree of a graph with 100 nodes is, where the probability of any two nodes sharing an edge is 0.04. And I just want the approximate value. Is it 1, 2, 3, or 4? And one final quiz for this segment. Going back to the NetLogo model, I would like you to pick some probability of two nodes sharing an edge, and it's your choice, but I'd like you to keep it constant. And then I'd like you to vary the number of nodes, starting with a small network, generating that network, and then increasing the size of the network, the number of nodes, while the probability stays constant, and then answering the following question. Does the average degree stay the same, increase, or decrease? What insights did this exploration of the Erdős-Rényi random graphs yield? Well, we saw some things which we will delve into further about when the average degree is very low, observing many disconnected components. We also saw the absence of hubs. The Erdős-Rényi random graph does not yield networks where some nodes are very well connected while most others are not. And we will explore these kinds of models that can generate such degree distributions in other segments this week.